In this video, I'm going to be talking about the valence shell electron pair repulsion theory and what that means and how the hybrid orbitals will help you understand more about the way that the molecules form certain shapes oriented around each atom. So I've created a document. I used many of the images came from an online textbook that had a really good connection between the atomic orbitals that we go over in orbital diagrams for atoms and ions, and then what happens to those orbitals and how they change, and they're illustrated as similar images for hybridization orbitals. And so we're just going to continue the discussion and try to think about the orbitals kind of in the same ways that we did with electron configurations and orbital diagrams. So most people have heard of a hybrid, especially with cars and with plants, but there's also that same term that applies for bonding and orbitals. And so what a hybrid is a combination of two or more different things, and it produces a substance that is a little bit like all of the original pieces. So I often kind of describe a person like myself. I'm a hybrid of my parents, and they are hybrids of their parents, a little bit like each of the parents. They come together and you get a hybrid. Well, hybridization with orbitals is a little bit different than that. There aren't parent orbitals. What hybridization is, if we start with atomic orbitals are the s, p, d, and f orbitals that we talk about that are present in atoms, but they're only present in individual atoms or monoatomic ions. If something has covalent bonds or metallic bonds, these atomic orbitals in the outermost energy level don't exist the way that we had thought of them originally. Hybrid orbitals are only formed when atoms create covalent bonds. There is one atom or one element that doesn't create hybrid orbitals, and that is hydrogen, because it doesn't have any other orbitals to combine with to create new orbitals. It only has the s orbital. Hybrid orbitals are created using the spaces that are present for the atomic orbitals. And so orbitals are really just space around an atom, and they exist at different distances from the nucleus. Well, the hybrid orbitals are in those same spaces. They just take on new shapes. And so they are in the same spaces, however, the shapes and orientations are very different from those of the atomic orbitals because they've changed. A set of hybrid orbitals is generated by combining atomic orbitals. The number of hybrid orbitals in a set is equal to the number of atomic orbitals. So if you use the spaces for 3 atomic orbitals, you create 3 new hybrid orbitals. The new set all have equivalent shape and energy. The type of orbitals that form in a bonded atom depends on the number of electron pair geometry as predicted by the VSEPR theory. We're going to look at it the opposite way. We're going to think about hybridization and let that help us predict what the geometry is. Every atom or every bond and lone pair in a covalent structure must be in either a hybrid orbital or an unhybridized atomic orbital. So if you have electrons in a Lewis structure, the actual substance that you're trying to draw, those electrons that you drew have to have an orbital for them to exist in. So if you draw a molecule and you put too many electrons in the valence shell for an atom, it will not occur that way because there aren't orbitals present in the outermost energy level for that atom to hold those electrons. Hybrid orbitals overlap to form sigma bonds. Unhybridized atomic orbitals overlap to form pi bonds. So anything that has a double bond or a triple bond, there's one bond between the atoms, that is the sigma bond. any additional bonds, the second or third bond between the same two atoms, would be created using atomic orbitals that haven't changed, and those bonds are called pi bonds. So there's a very limited number of regions and hybrid orbitals that we can create. There's only 2, 3, 4, 5, and 6 regions. So if you have an atom and there are bonds, the sigma bonds that go to an atom, and lone pairs on that central atom, every one of those atoms that it's bonded to and lone pairs that are on the atom need a region. We use the number of regions to help us figure out how many atomic orbitals are used, those spaces are used to create new hybrid orbitals. And so if an atom only needs 2 regions, then it will use the space for one of the s orbitals, the outermost s, and just one of the 3 p orbitals. And it creates 2 hybrid sp orbitals. And the letter sp is now the identity. So the original identity was s and p, and then it creates sp. It forms a linear shape with a 180-degree bond angle. If there are 3 regions, then we need 1 s orbital and 2 of the p orbitals, and that'll create 3 new orbitals. So you need 3 regions. You create 3 new hybrid orbitals that are called sp2 orbitals. That takes on a trigonal planar geometry, and it has 120-degree bond angles. If there needs to be 4 regions, then we need to use the s orbital, all 3 p orbitals, and that creates 4 hybrid orbitals, and the hybrid orbitals are called sp3 orbitals. And it creates a 3-dimensional structure called tetrahedral, and the bond angle is about 109.5 degrees. If there is an atom that can have more than 4 regions, then we can go up to 5 or 6. And if you need 5 regions, every one of these new regions has to have space created by orbitals that exist. And so we need 5 orbitals. We need one s orbital, 3 p orbitals, and 1 d orbital. That creates 5 new orbitals, and those orbitals are called sp3d. And the shape is called Trigonal Bipyramid, and there's 2 different bond angles. There's a 90-degree bond angle and a 120-degree bond angle, because there's 2 different planes. There's a linear plane going through the top and bottom, and then there is a trigonal planar plane in the center. And so from this plane to the top is 90 degrees, and within the trigonal planar center, there's 120 degrees between the angles. And then the largest geometry has 6 regions around it, and atoms that can have 6 regions around it, in order to create those 6 hybrid orbitals, they have to utilize the space for the s, all 3 p orbitals, and 2 of the d orbitals, and it creates 6 new hybrid orbitals called sp3d2, and it creates a geometry called octahedral, and all of the bond angles in an octahedral shape are 90 degrees. So we're going to look through each of these individually. We're going to talk most about 2, 3, and 4 domains. The 5 and 6 are not as common, especially if you go into organic chemistry. You only deal with 2, 3, and 4 domains. So if you need 2 domains for an atom to have lone pairs and bonded atoms, so you count lone pairs and bonded atoms on a structure in just one atom. If there's just 2 atoms bonded to that, then it just needs 2 domains. And so in a structure you would have s and p orbitals. This is just normal atomic. But then if they hybridize, if it needs 2 domains, you need 1 s orbital and 1 p. And so the s orbital in one of these p's forms a hybrid, and there's 2 new orbitals created. Both of those are called sp. And then there's 2 p orbitals left over. So it started with 4 orbitals, and it still has 4 orbitals. 2 of them are the hybrid orbitals, and 2 of them are unhybridized. If you look at the shape of them instead of the orbital diagram look, the shape in s orbital is just a sphere. one of the p orbitals, we're just looking at one of them, it's just a lobe. So if these two orbitals hybridize, then these are the two new orbitals that are created. They look a little bit like each other, but very different individually from each of these. And so this is one of the sp orbitals, this is the other sp orbital, and they're on the same atom, so they end up being directly across from each other, or 180 degrees. One example of a substance that forms a linear arrangement with sp hybridization is beryllium hydride. Beryllium is a metal, but its electronegativity is high enough that when it bonds to hydrogen, instead of forming an ionic bond, it actually forms a covalent bond. Polar covalent, but in this case, it ends up being nonpolar because hydrogen is on both sides. So if you look at this, we have beryllium in the center, and the way you figure out hybridization is you look at how many atoms are bonded to the center atom. So beryllium has 2 atoms bonded to beryllium, and it has no lone pairs. And so that ends up being, you need 2 domains. So if you need 2 domains, that means you need 2 hybrid orbitals. And the hybrid orbitals are what are used to create the first covalent bond between 2 atoms, or hold any lone pairs that are on an atom in a covalent structure. And so the beryllium needs 2 hybrid orbitals. So beryllium has S, its outermost energy level is 2, it has 2s and 2p. So it has 4 orbitals. It only needs 2 of those. So the s and the p, they hybridize, they come together, so they end up having 2 new orbitals created that are identical, have the same energy. This diagram here is just showing the energy. These are lower and these are higher in energy. When they come together, the energy of the hybrid orbitals will be in between the energy of these two, so that's why it's in between. But the leftover p orbitals that did not change, those have the same energy as they had before. They're unchanged. And so this beryllium hydride, it creates 2 hybrid orbitals to form those covalent bonds, and those hybrid orbitals are called sp orbitals, and it forms a linear geometry. The next shape is generated when there are 3 domains. So if there are 3 domains or regions around the center atom, those, you need 3 domains if you have lone pairs or bonded atoms, and those add up to 3. And so if something has 3 domains, for its atomic orbitals it would have s and p orbitals, but it would need 3 identical ones. So for sp2, you use an s orbital plus 2 p orbitals and that creates 3 new sp2 hybrid orbitals and 1 unhybridized p orbital. So 2 of these p orbitals, the spaces for 2 of these and the space for an s orbital, they all combine to create 3 new orbitals. The energy is between the original s and p orbitals, and then there's 1 p orbital that did not change at all, and so it's unhybridized. Shapes, you have 1 s orbital, a p orbital, and another p orbital. Those 3 individual orbitals create 3 identical looking orbitals, and when you put them on the same XYZ axis, they end up generating a shape that's called trigonal planar. So they're all on the same axis. They're all on the same plane. Some examples of substances that have 3 domains. We have this boron with 3 hydrogens on it, and so the number of atoms that are connected to boron is 3, and so it would need 3 orbitals. And if you have those 3 orbitals, then the boron, you would use its s orbital and 2 of the p's to create the sp2, and so each of these would be an sp2 hybrid orbital. This nitrogen here, it has an oxygen and a chlorine, so that's 2 atoms, and then it has 1 lone pair. So the domains is generated by looking at atoms. The nitrogen has 1 oxygen atom bonded to it, 1 chlorine atom, and then you also add lone pairs that are on the atom, so that gives you 3, so it needs 3 orbitals. This carbon here, this is formaldehyde. The carbon in formaldehyde, it has an oxygen bonded to it, and it has 1 hydrogen and a second hydrogen. So that carbon, its hybridization would be sp2. And then here we have each of these carbons needs hybrid orbitals. So this first carbon right here, it has a hydrogen, another hydrogen, and a carbon bonded to it. So it has 3 atoms bonded to it. So this carbon here, its hybridization would be sp2. And then this carbon, it has a hydrogen, another hydrogen, and a carbon. So it also needs 3 domains. So it would need orbitals to create sp2 orbitals so that it could spread out these atoms around the carbon. So each of these center atoms, this boron, this nitrogen, this carbon, and this carbon, all have hybridization of its valence shell of sp2. Each one of them also has an unhybridized p orbital. This nitrogen uses that p orbital to create that second bond to oxygen. This carbon uses it to create the second bond to oxygen. This carbon uses it to bond to that carbon, and this carbon uses its unhybridized orbital to bond to that carbon. And so each of these structures, the unhybridized p orbital is used to create another bond. This boron doesn't use its unhybridized orbital. The next number of domains is 4. If there are 4 domains that are needed, and that is if you have lone pairs and atoms that are bonded to a substance, to an atom in a structure, if there's 4 of those, so 4 atoms or 3 atoms in a lone pair or 2 atoms and 2 lone pairs, then the hybridization is called sp3. And it is created when you take an s orbital and the p orbitals and you use all 4 orbitals. So if you need 4 domains, you need 4 orbitals. So you use the s and then the p. You don't use inner s orbitals. Only the ones in the outermost energy level are the orbitals that can form hybridization orbitals and create covalent bonds. And so it'll create 4 new orbitals that are all identical, that are a little bit like the s and a little bit like the p, but they take on an equal amount of energy. That, again, that's why the energy is showing the s orbital has lower energy, the p orbital has a little bit higher energy. The orbitals they create are in between the energy, and this 1s, the inner energy level, that does not change. It's still just 1s. A picture of the actual shapes. So an image of an s orbital looks like a sphere. Each of the p orbitals looks like a lobe. So there's one of the p orbitals, there's another, and there's another. They're on the x, y, and z axis. All 4 of these orbitals create 4 identical orbitals that are oriented in different directions. And so here's one of the sp3 orbitals, here's another one, and here's another one. So one's on the z, One is in between, close to the X. Here's one that's close to the Z, following the other way, and here is one that is facing the opposite, that's close to the Y-axis, but it's not on the X and the Y, and this is not on any of the axis. The only one is this one right here is on the Z-axis. The other ones are in between. What it does is it creates a three-dimensional shape called a tetrahedral. It is one of the most common geometries for very common molecules. So one example is ammonia. Ammonia has one lone pair and then 3 hydrogens bonded to the nitrogen. So that's 4 domains. So what happens with the nitrogen atom is the nitrogen atom uses its S and P orbitals in the second energy level. Those spaces are used to create 4 sp3 orbitals. One of the orbitals has a lone pair, and the other 3 orbitals are used to create bonds with hydrogen. So hydrogen has 1 electron, the nitrogen has 1 electron. The new orbitals overlap with hydrogen's orbital to create that covalent bond, and so then you end up having a pair of electrons between it. This is a lone pair though, but it is in a hybrid orbital. Water also forms a tetrahedral geometry for its electron domains because it has sp3 hybridization. It has 2 lone pairs on oxygen and 2 atoms of hydrogen. It's 4. So hydrogen, its 2s and 2p orbitals form 4 new sp3 orbitals. And so 2 of those sp3 orbitals have lone pairs, and 2 of the sp3 orbitals are used to create covalent bonds. Methane, it has 4 hydrogens bonded to the carbon, and so 4 atoms, no lone pairs, so it needs 4 domains. So carbon will use the s and the p orbitals in the second energy level to create 4 sp3 orbitals that will space the hydrogens out equally around the carbon so that each of the bonds has room, and create that tetrahedral geometry. There are some structures where an atom can hold more than 8 electrons because it has d orbitals. So it has to be something that its outermost energy level is energy level 3 or 4 or 5. These are atoms that have empty d orbitals. And so if an atom needs to hold many lone pairs or form more than 4 bonds to atoms, then it will become what's called hypervalent, so more valence electrons. These occur and create 5 or 6 domains that are needed. They're needed because the total of lone pairs plus atoms bonded to the central atom would be 5 or 6. That's as high as we go though. So if you need 5 domains, then you would use the s orbital, all 3 p orbitals, and then 1 of the d orbitals, and that creates 5 new orbitals, and the orbitals are called sp3d. And so here's an image where each one of these yellow lobes is an individual sp3d orbital. So there's 1, 2, 3, 4, 5. This is on a 1-dimensional screen, but it is a 3-dimensional structure, and it's called Trigonal Bipyramid. Each of these Lewis structures is in the sp3d hybridization. Here this sulfur has 1, 2, 3, 4 atoms and 1 lone pair. That's 5 domains. This chlorine has 3 fluorine atoms bonded to it, and then it has 1, 2 lone pairs. That's 5 domains. Here this ion has 4 fluorines bonded to the chlorine and 1 lone pair, so that's 5 domains. Each of these would need hybridization on the center atom of sp3d. They can form the sp3d hybridization because each of these atoms, the outermost energy level is energy level 3. Then if you have 1 more atom or 1 more lone pair on that center atom, you would need another orbital, and so that's when you would get 6 domains, and those are created when an atom uses the space for s, the 3 orbital spaces for P and 2 of the orbital spaces for D. That creates 6 new orbitals. Each one of the 6 orbitals is called sp3d2. So the next video that I'm going to do, I'm going to go through and look at a structure that we draw, count the atoms in lone pairs, figure out the hybridization, what the geometry is, what the bond angles are, and we'll use this summary table at the beginning of this so that we can write down the electron geometry, and then we'll talk about the molecular geometry as we go through that.